Okay, in this lecture, we're going to talk about the related concepts of accuracy and precision. Now, these are important ideas, but we're going to talk about what makes them different. Now, we've already said that science is about testing, and when we are talking about testing, generally we're talking about measuring something. And so we've also said that, you have to have something that's repeatable. You need to be able to repeat the results of your experiments. You need to be able to communicate to other scientists what you did so that they can attempt to repeat your results and verify the veracity of your experiments. And so we need a language for communicating things about the quality of our measurements. And when we do that, we are going to use two very important ideas, the idea of accuracy and the idea of precision. Now, in a certain sense, accuracy means how close you are to the right answer. Generally, when we talk about the accuracy of a measurement, we're referring to how close the value we measure is to something that is known or some accepted value. And accuracy can refer to an individual measurement or to aggregates of multiple measurements. Now let's talk about an example here. We have the acceleration due to gravity has an accepted value of 9.81 meters per second squared. Now, we're actually going to learn about this later in the course, and we'll learn about what those units mean and what the number tells us. But all you need to know at this point is that there's some quantity and it's known. It's been measured many, many, many times, and we know that the value is 9.81 meters per second squared. Now let's say you go in the lab and you do some experiment and you measure the acceleration due to gravity, and in 3 measurements you get these 3 values. Are these values accurate? So 9.81, that's about 10. So if we look here, 1 meter per second squared, I don't think anyone would say that that's an accurate measurement. That's off by a factor of 10. Now, there are certain things in science where that would actually maybe fly. There are certain measurements in astronomy that if you're within a factor of 10, you're pretty happy about that. But for most things, that would not be considered an accurate measurement. What about 10? We said 9.81 is about 10. 9.76, it's also about 10. It's also, about 9.81. Would 9.76 be accurate? Would 10 be accurate? Both meters per second squared? The answer is it depends. When we talk about accurate, what we're really talking about is how close these values are to the value we want. Now, the usual way that we quantify accuracy is through percent error. We can mathematically compare a measured value to the accepted value using the so-called percent error formula. And you've probably seen this in some of your high school science classes before, but the percent error formula is you take the accepted value and you subtract from it the measured value, and then you divide it by the accepted value. And the absolute value bars here just mean that you want to make sure that whatever you do is positive. If this number were bigger and you subtracted, you get a negative number, but we don't want to care about that. So we always take the absolute value, so it doesn't matter which number is bigger. We just subtract them, divide by the accepted, make it positive, and that'll give you a fraction, which you then multiply by 100%. So let's look at an example. Let's say in a lab we used a pendulum to measure the acceleration due to gravity, and we're actually going to do that experiment in lab later this semester. And let's say we measure that, and the average of all our measurements tells us that the acceleration due to gravity is 10.1 meters per second squared. How close is that to the accepted value of 9.81 meters per second squared? Well, to find out, we can simply plug the numbers into the formula. We can say 9.81 meters per second squared minus 10 meters per second squared. That's going to be the difference of those two values. And then you divide it by 9.81 meters per second squared. And what you get is you get something like 0.0296. You multiply that by 100%, and you end up with 2.96%. And that is the percentage showing you how close your measured value is to the accepted value. And one thing that we can note here is that I've got every term in the top has meters per second squared, and the bottom term has meters per second squared. So there are no units in your answer. It's not 2.96 meters per second squared. It's just 2.96%. It's a measure of how close your measured value is to the accepted value. In other words, it's how close your measured value is to the right value, or how accurate it is. Now, precision is a different concept entirely. Precision describes how close a set of measurements are to one another. Not how close they are to the right answer, but how close they are to each other. Precision also tells you about the reproducibility of an experiment. In other words, if I do the experiment and then I do it again, are the numbers I'm going to get, will they be close to each other or will they be far apart? If I'm always getting numbers that are close to each other, that would be a very precise experiment. And I could rely that if I do that experiment in the future, I should expect the value that I get to be close to all the other values. If, however, the values I get are all over the place, then that would not really be a very reliable experiment. It's not a very precise experiment. And as we see here, precision can depend on the instrumentation used for making the measurements. Now, if we want to look at how close two numbers are together, where one of them is not an accepted value or a known quantity, we can use percent difference instead of percent error. And the way that we calculate percent difference is we use a different formula, but one that's very similar. I've got two measurements. Neither of these measurements are known. Now, this could be two measurements made by the same technique, or maybe you're measuring the same thing by two different techniques and you want to see how close you are to each other. That is the difference of the two measurements, and they are divided by the sum of the measurements divided by 2. Now, that looks like a really complicated formula, but it's really not. It's just the difference divided by the average. M1 plus M2 divided by 2, the stuff in the denominator here, that's just the average of M1 and M2 together. And so you take the difference, you divide it by the average, and you multiply it by 100%. Now, in the previous formula, the percent error formula, you took the difference and you divided by the accepted value. But here we've got two measurements, neither of which is accepted. And so we don't want to divide by M1 because M2 might actually be closer to the right value. And we don't want to divide by M2 because M2 might actually be closer to the right value, or M1 might be. The point is, if we divide by the average, we're comparing the difference to something that is maybe closer to the correct value than either of these together. So again, percent error is the formula you use when you're comparing a measurement to a known value or an accepted value. Percent difference is a technique you use to compare how close two numbers are to each other, two measurements, for example, to each other. So let's say two people measure the length of a rod to be 1.07 and 0.292 meters respectively. How precise are those measurements? Well, if we subtract them to get the difference, we find the difference is about 0.15. And if we average them together, we get the average is 0.995. And so if we divide the difference by the average, we get about 15%. And so that's not a very precise measurement. I mean, 15% is not crazy bad, but it's generally we prefer things to be a little bit better than that. But of course, that's going to depend on what instruments you're using and also the skill of the people using those instruments. And last, I like this dartboard analogy. It's widely used. I didn't come up with it, but a lot of people use this for sort of distinguishing between accuracy and precision. And so we've got three cases here, and they're sort of represented analogously by dartboard and darts. And so if you think of the bullseye as being the, what you're shooting for, if you hit the bullseye, that represents that you've accurately measured. you've measured the value close to what it's supposed to be. And so here we see all the darts are hitting the bullseye. That means that they're all accurate measurements, and we see that they're all close together, so they're very precise measurements. Now, then the next figure, we see the darts are all close together. The measurements, what the darts represent the measurements are all close to each other, so we would say those are measurements with high precision. So, are they accurate though? They're not. They'd be accurate if they were over here, but they're far away from the accepted value, the bullseye, so that while they're very precise, they're not very accurate. You guys might know from past experience, if you want to say measure the mass of something on a balance, the first thing you have to do is check that the balance reads 0 when there's no weight on it, when there's no mass on it. If the balance is off when there's no mass on it and you add mass, the balance is going to give you the wrong answer for the mass. So if you made a bunch of measurements of masses and you didn't zero the balance, all the measurements could be all close together, but they could be very far from the exact value because you didn't use the instrument properly. So that could be an example where you might get high precision and low accuracy. Now here we see low accuracy and low precision. All the darts are spread out and none of them are hitting the bullseye. And even if one of them did hit the bullseye, it's probably dumb luck. It's not because it's a well-designed experiment. If this is what you see in your experiment, that is an experiment that has gone awry. So if you see this, it might be something that's fixable, like, go back and zero the balance and take your measurements over. But this is what you're always shooting for. In an experiment, you want to have high precision and high accuracy whenever those things are possible.